All right, for this section of notes, we're going to go over, keep continuing on with this unit, and we're going to talk about the types of particles, types of compounds, and Lewis diagrams. So we're going to cover that. This is going to cover a couple of pages in your unit packet. I believe it's page 7, all the way to about half of the kind of first half of 11. So quite a few pages there, which is great. A lot of good practice here. So the first thing I want to talk about is particles. So when it comes to particles, they usually classify into 3 types. You've got neutral atoms. So that's just an atom kind of by itself. They have the same number of protons and electrons. I'm actually saying the same number of protons and electrons, not neutrons. Neutrons is wrong. Sorry about that, typo. And they're not bonded to other atoms. So a great example of this would be like sodium. Sodium by itself, it's a metal, it's shiny, and it's just an element by itself. So that would be an example of a neutral atom. An ion is an atom or a polyatomic ion, so a molecule that has fewer or more electrons that has a charge. So for example, sodium can also be an ion, and it has 1 fewer electron than it has protons because it has a +1 charge. Another example of this might be phosphate. Phosphate is a polyatomic ion, and it is negatively charged. It's made up of more than one atom. It's a molecule, but as a total group, it has a charge to it. It has 3 extra electrons than it normally would. The last type are molecules. So molecules are atoms that are covalently bonded together, and they share electrons. So an example of a classic example of that would be water. Water is a molecule that has covalent bonds. Ions can form compounds as well, but they are known as ionic compounds, and they are really just ions that are closely associated together. So for example, like sodium phosphate is actually just a bunch of ions. I didn't actually need to put those parentheses there, but there you go. So it's actually 3 sodium ions and 1 phosphate ion that kind of form a group of ions that just kind of stick together. So that's the basic definition of that. Okay, so the next thing to kind of think about are compounds. So as soon as particles start coming together, they form compounds. We've already seen 2 examples here of ionic compounds and covalent compounds. So to help you with this one, let's hop into YouTube real quick. I'll show you, there's a great video for this. It's this one, how atoms bond. I'll make a link in this video as well, but it'll be right after, when I finish recording this video, I'll put it in this list. And I'm not going to have you watch the whole thing, but it gives you a really nice example of how a ionic compound occurs when you have 2 elements that are 2 atoms that interact with each other and exchange electrons. One takes the other one's electrons. And now, so like for example, sodium, if it interacts with chlorine, will give up one of its electrons to chlorine, and they form 2 ions that then attract each other. And that's what a compound is. There's lots of examples of that. Another example is, and when sodium and chlorine form together to form salt, they kind of form this 3-dimensional lattice structure. And it's all about the ratio of sodium to chlorine atoms. But they're still ions. They're not really molecules. They're not actually bonded together. They're not sharing electrons. However, there is an example of that. If you have 2 hydrogen molecules, or atoms, pardon me, that come together, they will share each other's electrons and become a molecule. And this sharing here represents a bond, which we draw as like a line. So there's a whole bunch of examples of that. DNA. Here's a couple more examples of complicated molecules. And those are called covalent molecules. So those are very different from each other. It goes into a little bit. This is a great video to watch. I would highly recommend it. Just kind of keeping the difference between the two separate. They are really different. So let's, we've got some notes on this that you can take. Okay. So ionic, again, is a cation and anion electrostatically attracted to each other. I'll move this, see, hopefully you can see all of that. Attracted to each other involves electron transfer, not sharing. Ions separate when not solid. So if they are liquid or if they're dissolved in water, those ions will separate out. They won't be stuck together anymore. Only when they're solid are they really stuck together. Definitely not as a gas. Okay, covalent is when two or more atoms share electrons to form bonds. These bonds are not broken during phase changes. So like water, for example, when water evaporates, it's still water, still H2O. And they tend to all have a lot of high electron affinity, all the atoms in covalent molecules. So they tend to be on the right side, the upper right side of the periodic table overall. Metals, not so much, because they have much lower electron affinities. So it's easy for them to just give away their electrons, and it's easier for non-metals to just snag their electrons because they have a higher electron affinity. Okay, the last type, excuse me. Oh, man, tired today. Is a metallic bond. And a metallic bond, I can show you this video. This is also in on YouTube, and I'll post it. It's when metals all interact with each other. These are also known as alloys. Let's see.
Metal atoms have few electrons in their valence shell, and these are relatively weakly held.
So
the ionic solids have very different properties to the ionics.
So what kind of happens with the metallic bond is all of the nuclei sort of share all of the electrons in what's called a sea of electrons. So all the electrons just kind of end up flowing around each other. This is why metals conduct electricity really well and why they conduct heat. Because of this reason, let's see if we can get a good, yep, there's the conductivity thing. Yeah, so this is a really good animation that shows the sea of electrons. There you go.
This is because the loosely held valence electrons of metal atoms are delocalized. They are not bound to one atom.
So again, there's not a high electron affinity. So each individual nucleus doesn't have a ton of force, according to Coulomb's law, that holds it together. So those electrons just kind of flow, especially the valence electrons just kind of flow around, which is what all those little sparkles represent. It's called delocalized because they're not local. They're not like localized to one area. They're spread out. And they just kind of flow like water, like an ocean or a sea.
Instead, they can move through the lattice in all directions. A sea of delocalized valence electrons surrounds the crystal lattice of the cations. The structure is held together by the strong electrostatic force between the sea of valence electrons and the metal cations. This is called metallic bonding.
Yeah.
The electrons are constantly on the move, so the bonding acts in all directions.
Yeah.
Metallic
bonds are also known as alloys. So if you mix, like for example, jewelry, if you have gold jewelry, it's not 100% gold because gold is too soft. It's always mixed with like silver or copper. And depending on the ratios, that's how you get different colors of gold, like rose gold or white gold. So let's hop back in here. Sorry, I just found it. I just realized what we needed to do here. I do have another slide, part of the slide for you. So metallic bonding is, come on. Electrons and atoms of metals move freely between all nuclei in a sea of electrons. Alloys are multiple elements. They explain their high electrical heat and conductivity and malleability as a solid. So if you smack a piece of metal, the electrons or the nuclei sort of have a cushion within this sort of sea of electrons that they can move in, so they don't break. They're not very brittle. They just kind of, you can hammer pieces of metal flat or stretch it into a wire. Okay. So those are the three types of compounds. So let's take a quick moment here and let's go to our unit packet because there's a couple of quite a few questions that come from this. Page 7 right here is all just asking you if something is ionic or covalent. It's really important to know the difference. Ionic is a metal and a nonmetal. Covalent is a metal or two nonmetals. And they also say something called both. These are technically all ionic. So ionic is okay for these two, but they have a polyatomic ion, and polyatomic ions are actually covalent molecules. They're just covalent ions. So they're still considered ions. So for example, calcium chloride. Calcium is a metal and chlorine is a nonmetal. So therefore this is ionic. You could put I or ionic, whatever works for you. CO2. Carbon and oxygen are both nonmetals, therefore this is covalent. Barium sulfate is ionic, but you can also think of it as both because sulfate is covalent. But the overall molecule, the overall compound is ionic. Okay, so I think you can go through these pretty quickly and come up with ionic versus covalent. Hydrogen, we generally think of hydrogen as a non-metal. Hydrogen can be a metal, but generally it's a non-metal. So this is definitely covalent. Water is definitely covalent. It's a molecule. Okay, so there's that. The next two pages, let's go over them real quick. This is page 8, you can barely read that, and 9. These are going over the difference between ionic and covalent bonding. So page 8 is ionic bonding, page 9 is covalent. And the idea behind this is really, I want you to really draw out, just like these examples, how an ionic compound is different than a covalent compound. So in this one, for example, they're showing that you start with the Lewis dot models of both the elements and you show what's happening. So these ones are all ionic. So they can show, for example, here that this sodium just has one valence electron. And again, remember that because we wrote it at the top of the periodic table here, how many valence electrons? It's 1, 2, 3, 4, 5, 6, 7, 8. Okay. So sodium has one valence electron, chlorine has 7. Sodium gives an electron to chlorine, or more accurately, chlorine has a higher electron affinity than sodium, so it is able to outcompete for that electron. Sorry, just getting lights back on. And then it causes both of them to become ions, pardon me. And then those two ions are electrostatically attracted to each other because they have opposite charges. Same as the same Coulomb's law that explains how protons in the nucleus attract electrons in the electron cloud. Same thing here. For calcium chloride, calcium has 2 valence electrons. Each chlorine has 1 valence electron. So calcium can get rid of both electrons by giving each one to a chlorine. We end up with 2 chlorines and there's a negative charge, and the calcium's a 2+, and they're all attracted to each other. So let's go over, I'll go over 2 examples with you. Maybe just one for now. Let's do number 2. I like number 2. So magnesium, let's start by drawing out the Lewis structure. Magnesium has 2 valence electrons. Okay. Iodine has, it's here, so 7. So 1, 2, 3, 4, 5, 6, 7. And if you remember, you have to draw 1 on each of the 4 sides before you can start pairing them off. That's one of the rules. So what's actually going to happen here is that magnesium is going to donate this electron to this iodine and this electron to the other iodine. And what will happen is you're going to end up with magnesium that is a 2+ charge. And each iodine is going to have a -1 charge because they gained electrons. Magnesium lost 2 electrons, hence the 2+ charge. And this is kind of the, what's actually going to happen. So if you want to draw little circles around them to make it a little clearer, that might help. The overall formula is MgI2. Okay, so there's our visualization of what's actually happening, and this is the formula that we write for it. So that's kind of what I'm looking for these 5 problems. You can tell here that it doesn't tell you how many of each, it just says when magnesium interacts with iodine, it's going to have enough iodines to give up the electrons too. Magnesium has to give up 2 electrons. Iodine each one only needs 1, so you're going to need more than 1 iodine. And coming up with that ratio is obviously a big part of writing ionic compounds. Remember, back to Unit 3. This is all back to Unit 3. Okay, let's go over an example from the next page. This is a covalent bonding, and this is drawing Lewis diagrams for covalent molecules. So we're going to do more of this. I'm going to give you even more examples, but just to kind of get you started here. Again, we're going to write the Lewis structures and show how those electrons are shared and that bonds form. So, for example, here they have hydrogen and chlorine. Hydrogen has 1 valence electron, chlorine has 7. They each share this non-paired electron and bond together. Another way of writing this would be like that. So there's a chlorine, hold on, scratch that out. We can probably get these electrons in right there. Perfect. This bond is equal to an electron pair that they're sharing. So these 2 electrons become a bond, a pair of electrons. Let's try an example of this. Let's do, what would be a good one off this list? You know, we were just talking about water, so let's do water. So here's the formula for water. It's H2O. So the way that I like to draw this is I start by writing out all of my Lewis dot diagrams. So hydrogen has 1 valence electron. Oxygen has 6. So 1, 2, 3, 4, 5, 6. There has to be 1 electron on each side before you can pair them off. Doesn't matter how you pair them off, but there you go. And now we just need these electrons that are not part of pairs are going to kind of pair off with each other. So it looks like these 2 electrons and these 2 electrons are going to kind of pair off with each other. So now we need to put these together in a way that makes sense. Now, we're going to learn a lot more about why I'm drawing it in this particular way, but that's kind of the answer. Another way to look at it is like this. That's a bond. That's a bond with the 2 electrons. If you draw it like this, technically that's wrong, but it's fine for right now. We're going to learn more about why actually this is correct, but that's a whole nother story. We're getting to Vesper diagrams. That's the next set of notes. Okay, so I'm looking for something like this for these ones to show that they're bonding and sharing electrons, as opposed to ionic compounds are donating electrons, becoming charged, and then attracted to each other. But if you dissolve this in water, I think magnesium iodine will probably dissolve in water. All of those molecules or all those ions will just separate and go floating off and doing their own thing. Okay. I think that's pretty good for right now. Let's talk about Lewis diagrams, which is actually what this right here is. So there's a page here, page 10 on Lewis diagrams. This one's a little tricky, but page 11 has some pretty good stuff. So we're going to come right back to this. Now you're going to notice on your paper, I crossed out some of these. I've given them replacements. The ones that were there before were a little bit too challenging. We are going to do Vesper later, but that's not for right now. But we do have some good examples here, and we're going to do a couple of these. But first, let's go to the notes. Okay, so Lewis diagrams. Again, the way that you do this is models that show the bonding of covalent molecules. There's the octet rule, and They prefer to have 8 electrons. So that's kind of all of the elements except for hydrogen likes to only have 2, like to have 8. So if we're trying to draw a Lewis diagram for something like CH4, again, I recommend, first step, draw out your Lewis model of all of the elements. So I draw 4 hydrogens. Each one has 1 electron, valence electron. There's 1 carbon. It has 4 valence electrons. So there's carbon, 1, 2, 3, 4. And you're really just playing connect the dots. So you want to connect these individual electrons to the correct spot. And it looks pretty obvious to me that they're going to connect kind of like this. There's going to be 1 on each of these 4 sides. So the way I would draw that, put the carbon in the middle, put all the dots around. Okay. And it's just little puzzles you have to solve, and these connect. Each line represents 2 electrons, it represents a pair. And so each molecule should have, or each atom in the molecule should have the correct number of valence ones. For hydrogen, 2 is great. For carbon, it should be 8 total, the octet rule. So each of these represents 2, so that's 2, 4, 6, 8. So this follows the octet rule. Now, there are a lot of molecules that don't actually follow the octet rule. That's beyond the scope of our class for now, but it will definitely show up in AP chemistry. So some of the questions in your unit packet, these ones I kind of crossed out, are examples that don't follow the octet rule. If you're curious, I can teach you how to do them. Just ask, and I'd be delighted. It's not that hard. Okay, so let's try this next one. Let's try nitrogen trifluoride. So nitrogen has 5 valence electrons and fluorine has 7. So nitrogen is 1, 2, 3, 4, 5. So 1 pair of electrons and 3 unpaired electrons. And there's 3 fluorines. And fluorine has 7. So it's going to be something like this. And again, it doesn't really matter where the unpaired one goes as long as there's one that doesn't have pairs. Now, when you're playing connect the dots, generally speaking, as long as it doesn't break the octet rule, which is most of the ones I'll give you, you kind of leave these pairs alone. So we're not really going to touch those. Those are kind of already good. So we're going to leave these ones alone. It's the unpaired ones that need to get paired off. So it looks like we've got 3. Each fluorine has 1. The nitrogen has 3 spots. So now it's just a matter of arranging them in a way that makes sense. So maybe something like this. And I do need all these electron pairs. They are important. If you neglect to put them, I will get very upset. And we just, again, connect the dots. So it's just a puzzle. Again, we covered this in unit 3 or 2 or whatever it was. Yeah, we've covered this before. It was the compounds unit. Okay, so that's the Lewis structure for that. Now let's try silicon dioxide. Now silicon has 4 valence electrons and oxygen has 6. I just know this, but you can see it right here. Silicon has 4, oxygen has 6. So another good strategy is to always put the one with the most, that needs the most electrons, in the middle. So for example, carbon here needed 4 electrons, we put it in the middle. Nitrogen needed 3. The fluorines all needed 1, so we put the nitrogen in the middle. The hydrogens just needed 1, so we didn't put, we've saved them for last. So let's try putting the silicon in the middle. And I think what you're going to find is there's definitely going to be an oxygen on either side of it. So I'm just going to use pencil for a second because it'll be a little nicer, cleaner here. Okay. So it's pretty clear that these electrons are going to pair off this way. But we still have this electron and this one and this one and this one. So basically, bloop, those just have to pair off. This is called a double bond, and that's totally fine. There's nothing wrong with double bonds. They happen all the time. So what's going to end up happening, silicon is going to bond twice to that oxygen and twice to this oxygen. Oh, going back here for just a second, the nitrogen and the fluorines all follow the octet rule. The nitrogen has 1, 2, 3, 4, 5, 6, 7, 8 electrons because the bonds count as 2. The fluorines are 1, 2, 3, 4, 5, 6, 7, 8. So pretty good. Same thing here. Oxygens have 1, 2, 3, 4, 5, 6, 7, 8. Each bond counts as 2 electrons, so a double bond is 4. The silicon is 1, 2, 3, 4, 5, 6, 7, 8. We're good to go. Okay. So that is Lewis diagrams. Now, Lewis diagrams are really important to be able to do VSEPR models. So that our next step, you got to be able to do this. So let's do some more practice. Okay, this is page 11. If you have a chance, if you want to copy down some of these new problems, these are all ones that you're going to be able to do just to give you some of that extra practice. So we're going to start with this one. So we've got CH4, NF3, SiCl4, SiO2. CF4 is fine. HCN, PCl3, NH3, CO2, HI, OBR2, and N2. I'm wondering if we should change the HI one. Maybe we'll do something a little bit more fun. Yeah, let's switch that one out. Let's do, let's go C2H, hold on, I'm just counting. C2H5OH. Let's try that. So that'll be a fun one. Okay, let's start with CH4. Actually, we already did that one, so we don't need to do that again. Let's do NF3, we've already done. Moving on. SiO2, we've also already done. Let's do SiCl4. So again, silicon has 4 valence electrons. Chlorine has 7. And there's 4 of them. So 7, 7. And again, all 4 of these ways of writing chlorine are totally fine. The only electrons we care about are these and this little guy there, and this one and that one. And it looks like we've got 4 spots that need an extra electron. So that's going to be pretty simple. We'll put Si in the middle and a chlorine on each side. And all those valence electrons. And so each of these atoms will all follow the octet rule. The chlorines all have 8, 2, 4, 6, 8. The sulfur has 2, 4, 6, 8. Everyone's happy. Or silicon, not sulfur, I'm sorry, silicon, Si, silicon. Okay, cool. All right, let's try HCN. This is a fun one. Now we have 3 this time. So we're gonna have to figure out which one to put in the middle and how to do this. My first thought is always whichever one needs the most electrons, it's going to be carbon. So carbon, hydrogen just has 1 pair, so it just needs 1 more electron. Carbon needs 4. I gotta get the lights back on, hold on. There we go. Okay, carbon needs 4 and nitrogen needs 3. So let's put carbon in the center. And let's put kind of hydrogen on one end and nitrogen on the other. And let's see if we can make this work. I'm going to use pencil again because it's kind of nice for this. Hopefully, yeah, you guys should all be able to see that. So it seems pretty obvious. The hydrogen will be connected to the carbon like that. The carbon's going to be connected to nitrogen for sure like that. But then we can also just, hey, triple bonds. Those are a thing. They're real. You can make triple bonds. So just to draw that a little bit more nicely. That's the Lewis structure for HCN, which is a cyanic acid. Or no, cyanic acid, that is what it's called. Okay. Let's see, let's do one more. Let's do PCl3. So phosphorus has 5 valence electrons as well. And chlorine, once again, has 7. Again, it looks like we've got 3 spots. So each chlorine just needs 1 electron. The phosphorus needs 3. There's 3 chlorines. Throw the phosphorus in the middle and the chlorines around it, and we should be pretty much good to go. Very simple. Bloop, bloop, bloop. Done. 8 valence electrons each. All of these were good as well. The hydrogen has 2, the chlorine has 2, 4, 6, 8. The nitrogen has 1, 2, 4, 6, 8. Same thing here. Okay. Once you get used to doing these, it becomes pretty easy. These are going to be really helpful. Try to leave a little bit of room after each one for the VSEPR. So maybe I'll draw like a quick little like diagrammy thing here. So we have a little space. That one kind of got in the way, but we can try. So you have a little bit of space here for the VSEPR. We are going to come back to that for the next section, going from Lewis to VSEPR. Okay. Actually, we just have to label them, so it's not too bad, but we might want to redraw them. We'll see how it goes. All right. I think that's a good place to stop. I will pop into the YouTube just to show you a couple more resources. Both of these are really good videos as well. So what is the shape of a molecule? That's fun. Oh, that's more of that. Yeah. Bonding models and Lewis structures. This is 11 minutes long. That might be very helpful. Yeah. And these other 2 videos for sure. Let's stop there for right now, and we will continue on with geometries of molecules. One quick note, you'll notice that all of these Lewis structures are only covalent molecules because ionic molecules don't bond. So you don't have to worry about that, just covalent. So all non-metals here. All right. See you in the next video.